Hello everyone, we are Group 3 and we will be presenting to you a case study of the Walt Disney Company on the big data implementation in the tourism sector. Now let's start with our context and objective. The data challenge in tourism is global tourism generates massive heterogeneous data streams. The high density environments like Disney theme parks, operational efficiency hinge on the accurate analysis of attraction waiting times. So waiting time directly impacts the visitor satisfactions. So this case study will evaluate the Hadoop ecosystem's efficiency by simulating a real-world big data pipeline using the Disneyland dataset of over 100 rides. Our primary goal of this case study will be to benchmark the disk-based batch processing, which is the Hive, against the in-memory distributed computing, which is the Spark, for the tourism analytics. We have identified two problem statements, which is the computational latency and the architectural ambiguity. Under the computational latency, the traditional relational database management system architectures lack the horizontal scalability required to ingest and analyze the multi-dimensional tourism datasets without a significant latency. So current strategies often rely on static average, failing to capture the dynamic volatility of guest behavior influenced by the seasons and events. Next is the architectural ambiguity. There is a technical gap in understanding the cost-benefit ratio between the Apache Hive, the SQL on Hadoop, and the Apache Spark, the in-memory, for this specific domain, tourism domain. So we must determine if Spark speeds justify its resource intensity compared to Hive stability for historical batch reporting. Now we will have the next person for presenting.
Hello everyone, I'm Rehan, and now I'll be presenting the methodology behind our comparative study of big data processing engines. Our research focuses on a dataset containing over 3.5 million records of history Disneyland wait times. This data includes 14 attributes such as attraction names, timestamp, and seasonal metadata. To ensure a fair comparison, we deploy our infrastructure on Google Cloud Data Prop using an identical cluster configuration for both engines. Specifically, a master node and two worker node using N1 standard for machine types. And by keeping the hardware and storage system identical, we ensure that any performance delta is strictly due to the processing engine themselves. To determine which engine performs best, we are benchmarking for specific areas using this evaluation metric. Execution time, to measure speed, CPU and memory utilization to assess resource efficiency, code complexity to evaluate developer productivity, predictive model accuracy measures specifically using root mean square error, which is IMSE, for our wait time estimation. Next. So moving to our system architecture, we design a dual pipeline architecture that decouples storage from computation. We use Google Cloud Storage, GCS, as our signal source, ensuring both engines access the exact same raw data. The data then split into two distinct paths. For pipeline A, we are using Apache Hive. This represents a traditional disk-oriented batch warehousing approach. It uses a schema on read model via Hive Metastore to process large-scale aggregation using HiveQL. And for pipeline B, it is using Apache Spark. This is our in-memory processing powerhouse. Using PySpark and ML library, we go beyond simple batch queries to perform iterative workloads and predictive modeling for wait time estimation. So finally, the outputs are exported back to GCS and connected to Power BI for interactive visualization. So that's all from me. Thank you.
All right, now moving on to the performance evaluation. In terms of speed, Spark has outperformed Hive by 20% in terms of the end-to-end processing time. This is due to Spark's DAG optimization and in-memory caching, which significantly reduce the input and output overhead. While Spark is faster, it is important to note that it requires more complex code, around 100 more lines than Hive's simple SQL queries. And next. In terms of the resource utilization and efficiency, Contrary to the belief that Spark is overly resource intensive, our tests show that it manages a CPU more efficiently than Hive during processing tasks. However, the trade-off is high code complexity. Spark requires more boilerplate code for data frames, while Hive rely on straightforward SQL. Pass to the next.
Yeah, using Spark ML libs, we built a regression model to predict wait times. The gradient booster tree model performed best, achieving an R-square of 0.81, meaning 81% of wait time variability is explained by our model. The key predictor was historical demand patterns, accounting for about 60% of the predictive power. Next. Our model revealed that wait time can be 2.2 times longer during peak seasons, 46 minutes on weekends versus 21 minutes on weekdays. This has clear operational implication. We recommend dynamic stuffing, increasing operator by 2.3 times during peak windows, and surge pricing strategy like lightning lens pass to manage demand. Next will be passed to another person.
Hi, I'm Chin-Pei. I'm going to present the final part of our presentation, which is the conclusion and visualization using Power BI. In this project, both Apache Spark and Hive successfully processed over 2.5 million data and produced similar analytical results. For our comparative analysis, we have reached several key conclusions. First, Apache Spark clearly stands out as a better platform for analytics. Its in-memory processing and DAG optimization allow us to achieve a 20% efficiency gain compared to Hive. Spark handle computation-heavy tasks quickly and support advanced machine learning, such as our gradient boost model. Second, even though Spark is superior for analytics, Apache Hive is still important. Its SQL-based structure make it ideal for large-scale data warehousing and batch reporting. Third, our architecture of using Google Cloud Storage and Dataport proved to be flexible and scalable. To transform data into actionable visual insight, we built an interactive Power BI dashboard. The dashboard visualizes the population over weekend versus weekday, average waiting time by attraction, and the seasonal trends. This allows park manager to manage the park efficiently. Finally, looking forward to the future, our next step is to move from batch processing to real-time analytics. By integrating Spark streaming, Disneyland could eventually predict crowd surge instantly and adjust operation dynamically, such as redirecting visitors, deploying more staff, or pushing real-time notification to guests. In conclusion, our project demonstrates that Spark, Cloud Architecture, and Power BI work together, they form a powerful and scalable big data ecosystem. That's all for our presentation. Thank you.